All right, today's is similar to yesterday's. We did perpendicular bisectors, angle bisectors, and I mentioned there's two more. There's altitudes and medians. So it's the same kind of idea. It has to do with triangles. Okay, a median connects the midpoint of a side to the opposite or vertex. Okay? So, again, there are three types of triangles. You can have an acute triangle, you can have a right triangle, or you can have an obtuse triangle. So, when you do a median, it's easy to, like, there's four of these things that are all kind of similar, so it does get a little jumbled up. To draw in a median, you just kind of estimate where the middle is, and you connect it to the opposite vertex. So the only thing you have to label on these is that this is the median, that equals that. Sometimes when you do a perpendicular bisector, if it's an isosceles triangle, it will go through that like that. So this line and this line would be both a median and a perpendicular bisector. That only works though if it's an isosceles triangle. So then when I do this one, from the middle, connect the vertex, show that those are equal. Just like the other two yesterday, these three lines are concurrent, which means they'll intersect at one single spot. So if I draw this one in, it would go from there to there, from there to there, and it would go through there. So there's the point of concurrency. Here, the obtuse is always the hardest one to do. Oops. Okay, so when we did the perpendicular bisectors, that point, did anyone remember what that was called?
Point of concurrency.
It is the point of concurrency, but it's got an actual name.
The circumcenter.
Circumcenter. The angle bisectors was the circle goes inside, so it's the in-center. This point is called the centroid. Okay? Shh, quiet. It's called the centroid. Now this one does have an actual, well, I guess if you were going to do this, if you cut a triangle out of paper and you wanted to balance it sideways, you know, like tip this on its side, if you put your finger on the centroid, that's the balancing point of a triangle. So can everyone imagine that in their mind what I'm talking about? Yeah. If I cut this out and put it sideways like this and rest it on my finger, it would wobble, but if I put my finger on that point, it would be balanced. Oh. Now, okay? So, if this were just a total, you know, filled-in triangle, if I found the centroid of it, and I turn it on my side, put my finger on that point, it would balance. Okay? Now, we're obviously not going to do that, but the thing that we will do with this is you notice each median is split into two segments, right? Yeah. If you had to guess, if this length right here was 3 whatever, any guess what that would be? Keep going. 6.
Yeah.
The short segment is always half as long as the other segment. So if this piece here was 2, that would be 4. Okay?
4.
All right? Now, the way they show it in the book is this piece right here. Say this is labeled A, B, C. AB is 2/3 of the whole thing. Because if this is 3, I could split this up into 3 and 3, right? So there's 2 segments out of the 3 that are the whole thing. The shorter one, BC, is 1/3 of the whole thing. Okay, that's the complicated way to think of it. It's just easier to remember it this way, that the short piece is always half as long as the bigger piece, or vice versa. The bigger piece is twice as long as the short piece. Instead of, this is what the book will show you. Then we've got the altitudes. And once again, you can either have an acute, a right, or an obtuse. An altitude is a line from each vertex to the opposite side, but is perpendicular to the side. Okay? So if you're drawing in an altitude, you start at a vertex and you go to the other side, but it's got to be perpendicular to it. So again, if you had an isosceles triangle and I drew an altitude, this would be not only an altitude, it would also be a median, and it would be a perpendicular bisector. It would be all 3 of them. Okay? So when I draw this one in, if I go to the side, it's going to be right about there to form a 90, and then there to form a 90.
So it doesn't have to be in the middle?
We'll see. In this one, they're all in the middle. Obviously, if it's going to balance, it has to be. When I do this one, now remember what an altitude is, like in an airplane? What's an altitude mean? Height. So an altitude is just this. If you're measuring from here to here, this is how tall it is. And when you measure your height, you don't stand sideways, right?
No.
You got to stand straight up and down. So when you measure how tall it is, you measure from the bottom straight up to the top. If you tipped it then and you're measuring from here to here, this would be the height. And if you tipped it, so this was the bottom, this would be the height. So there's 3 different heights according to the triangle, however it's sitting. That's why they're called altitudes. So on this one, the way it's sitting right now, if I asked you how tall this was, you know what you'd look at?
The leg.
Yeah, the leg. From there to there. From the vertex to the other side, and it forms a 90. And then if I tipped it down, this would be the height. And if I turned it so this was the bottom, that would be the height. Does that make sense?
Yep.
So there, the point of concurrency is right on the corner. This is the hardest one to do of all the drawings. This is an easy one. From this vertex to this there's the height. If I tipped this upside down and this was the bottom, you'd measure up to the height. Now, how do I get from this vertex to this side, but it's got to be perpendicular to it? It's got to go outside. Think of this as like a gas station. If you think of this like a gas station where this is a lean-to, where people drive underneath, you know, if you wanted to measure how tall this building was, you would have to stand way out here, right? And you'd measure straight up. So what you got to do is you got to extend the side and measure how tall it is. So like this is the ground, so you'd have to walk all the way out here to measure up to see how tall it is. And then if this were the bottom and you were measuring to this peak, you'd have to extend this side and then measure up at it like that.
You're welcome.
Okay, now these will intersect also. I didn't put it high enough up, but if you kept going down, or maybe I did. Well, they would intersect down here somewhere. So that's similar to the perpendicular bisectors. Sometimes they intersect inside, sometimes it's on, sometimes it's outside. If you remember the perpendicular bisectors, if it's acute, they intersect inside. If it's right, bisect that, they intersect right on it. And if it's obtuse, they intersect it outside. Okay? So these two are similar in that sense. Now, the thing with an altitude is, it's got a point where they all intersect, and it's got a name. Can anyone guess what it is? It's the orthocenter. This is the one that I saw on an ACT test. And of these three things, the orthocenter doesn't do anything. It just has a name. Centroid, splits it into equal parts like this. Perpendicular bisectors find a point that's equidistant from three corners. The angle bisectors, equidistant from all three sides. This really doesn't tell us anything, other than how tall it is from one side to another.
It's just that where all the right triangles meet, basically.
Okay. So, the problems are fairly simple. This is why you need to know what the names of them are, though. R is the centroid, which means the medians are drawn. So what that means is this equals that, and this equals that. So that's why you need to know what the words mean. They tell us that SR is 16, right there. This piece right there. So they're wondering, what is SV and RV? RV is half of that, it's 8. So SV is the whole thing, it is 24. That's really what the problems are today, is like that. So you need to remember the centroid splits it into pieces where the small part is half as long as the big part. Finding a centroid. Here they've got a triangle on a coordinate system for you. They already drew in one median right there. Here's the triangle, DEF. Okay, so what's nice, if it's drawn correctly, we can find the middle of this side is right at G. Okay, it's up 3 over 2, up 3 over 2. Now, what they're going to have you look at is the midpoint. Okay, put your stuff away. Midpoint goes back to the beginning of the year. To find midpoint, it's x plus x divided by 2 and y plus y divided by 2, the average of the x's. 1 plus 5 is 6, divided by 2 is 3. 1 plus 7 is 8, divided by 2 is 4. So there's the midpoint. So when we draw it in, we just got to connect it there, and that would be the centroid then. 5 over 3 up. Okay? Okay, so I'll leave that up there for your assignment to look at, but is the orthocenter. Orthocenter is the altitude. On this triangle, inside, outside, or on it. Well, is that acute, right, or obtuse?
Obtuse.
It's obtuse. This angle's a little more than 90. So it is outside.
This is why you don't see. Shut up.
Okay, this is the centroid, which means these are medians. TU is 7. So what is QT? 14. And then they ask for the whole thing, QU, you just add them together, 21. Another type of question, you can just look at the picture. Is the orthocenter for an isosceles triangle always located inside the triangle?
No, wait, no. The right
Now,
triangle could be.
because yeah, you can have an isosceles acute triangle, you can have an isosceles right triangle, and you can have an isosceles obtuse triangle. So it's not always, the only time it is when it's acute.